So welcome back, everyone, to the Langtangen seminar. We're very happy today to have Professor Sid Mishra from ETH Zurich. Sid has many accolades. I'll just note a few of them. So he's been elected a Fellow of the European Academy of Sciences. He's a recipient of the Collatz Prize, the Dalkowitz Prize, and the von Mises Prize of GAM. He is the head of the Computational Applied Mathematics Laboratory at ETH Zurich. He is also the director of the Computational Science Zurich and a core faculty member of ETH AI Center. Sid has many interests in applied mathematics. As of late, his research interests lie in the fields of numerical analysis, scientific computing, and machine learning, with many applications including engineering, fluid dynamics, astrophysics, climate science, geophysics, and biology. So we're very happy to hear his perspectives today on scientific machine learning, and in particular, learning PDEs. And just before he begins, I'd like to remind everyone, if you have any questions, please put them in the Q&A, and then I will ask them at the end of the talk. So, Sid, the floor is yours.
Thank you very much, Thomas, for this kind introduction, and also to you and the other organizers for inviting me. It's a real honor to speak in this Langtangen seminar on scientific computing, because as I was telling Thomas, I spent quite a bit of time in Oslo in the middle of 2000s, in the aughts, so from 2005 to 2009. And during that time, I had the privilege really of listening to Hans Petter many times and was really impressed and inspired by his vision for efficient implementation of PDE solvers at that time, which ultimately led to the Phoenix project. So that was quite. It's a pity that he left us too early, but so for me, it's a real honor to talk here. So I'll talk about learning PDEs, which is part of the recent work that I've been doing. And to this audience, I think I don't need to introduce that PDEs are really the language of nature, and they model an immense diversity of physical phenomena, physical processes across an entire range of scales. So if you think of the tiniest scales imaginable, that of subatomic particles like electrons, the Schrödinger's equation, and if you think of really cosmic scales, black holes, for instance, and then you have Einstein equations, and everything in between. So PDEs really are the language of nature. And we also know very well that we can't solve them by hand, and we have to rely on numerical methods, find difference, find volume, find element, and so on. And it's here that Hans Petter's contribution, both in terms of his research as well as his exposition, books, and so on, really lay in. Right? So this is a very, very successful, very mature field. And I have my own little contributions to that. From my lab, for instance, as Thomas just mentioned, we apply these methods to astrophysics. So these are supernova explosions, waves from the sun, something that I did in Oslo back in the early 2000s, a long time back, engineering flows, clouds, tsunamis, and so on. So a whole spectrum. So these methods are extremely successful. So then the question that arises is, what's the catch here, right? If they're so successful, why do I need an alternative? And there are reasons, there are issues with these methods, and perhaps the most urgent one is that of computational cost. And instead of giving you sort of a long spiel about that, let me just explain one example. So this is a pretty simple example, straightforward example, three-dimensional Navier-Stokes at very high Reynolds number. So you have some initial conditions, there's a vorticity in the beginning, and then you get a very complex evolution of the solution at a later time. So this is the vorticity at a later time. And if I want to compute it at high resolution, this is a 1024 cube, so very high resolution. We have a optimally implemented spectral methods code, which can scale very well on GPUs. And on the previous supercomputer that we had in Switzerland, this took about 100 GPU hours per simulation, right? If I had done it on CPUs, like what we are doing in Oslo back in the day, this would have been like 50 times more and almost unaffordable. But the point is that this simulation, one single simulation is not really relevant here, because if you can see on the right, so you have this tiny little perturbations in the initial data. This is a chaotic system. The solution changes almost entirely. So it doesn't make any sense to look at a single simulation. What you need to do is to do uncertainty quantification, do multiple simulations, and then this becomes what is called a many query problem, where the PDE solver has to be queried many times. And most real-world problems are of this flavor. So you have uncertainty quantification, you have optimal control, design, inverse problems, where you have to call the PDE solver many times. So if you do that, and you need at least 1,000 samples to get some meaningful statistics, then this number becomes a humongously large number. It's 100,000 node hours for a single simulation. And this is quite unaffordable, right? But now you can say that compute is getting cheaper. There are faster and faster systems that are coming through. And for instance, our latest supercomputer in Switzerland is much, much faster. Even then, you see that instead of having 100 GPU hours, we got it down to 25 GPU hours. It's simply because these problems are memory bounded and you can only do so much with more compute. And if you do want to do an ensemble simulation, it's still very, very expensive. So I think I've convinced you, and I think people at Similar know this very well, that you really need to solve PDEs much faster than we are able to do at the moment. So this is the first sort of motivation or first caveat that we have with traditional numerical methods. The second one, which is I think even more important, is that you can use PDE solvers only when you know the underlying PDE, right? But if you think of real world problems, and these are sort of flows in the brain, something that Maria Rugnes at Simula does very well, reservoir simulations, something which is also very common in Norway, and of course in the Earth system, the point is that sometimes you don't even know the underlying PDEs. Perhaps you know it to some undetermined parameters, and sometimes not even that. So if you think of the Earth system, for instance, so the flows in the atmosphere and the ocean, these are modeled very well by Navier-Stokes equation. Radiation, for instance, is modeled well by the radiative transport equation. But you have many other phenomena. You have forest cover, vegetation, soil, land, aerosol, microphysics. None of these things can be modeled from first principles. You can't just sit down, write an equation of motion, a variational principle, and then derive the PDE, right? So what people do is a lot of ad hoc heuristics, and this leads to a lot of modeling errors. And in robotics, people call this to the sim to real gap. So there's a real gap in what a numerical solver provides, and because the physics itself, there's a big modeling error, and what the real world is, right? So this is sort of increasingly we see that the physics itself is unknown or is missing. So in that case, even if you have a very fast PDE solver, it's not going to be very, very useful. So in both cases, either when the PDEs are hard to solve or when they're unknown, what we can take recourse to is data. So we have data for the problem, particularly for the Earth system, we have a lot of data. And the idea is that can we leverage this data together with the physics and try to learn from the data the dynamics of the underlying system. So that is going to be the sort of the hypothesis, the posit of my talk today, where we are going to learn these PDE solutions from data and from physics. So this is going to be the objective. But in order to sort of proceed further, I need to make this problem better defined, more precise, and then I have to understand what does it mean to solve a PDE, right? There are different interpretations, but I think all of you will agree with me that a particularly powerful interpretation or particularly powerful encoding of this is if you can find the solution operator of a PDE. Because at the end of the day, if you have a steady state elliptic PDE like this, the solution operator maps, for instance, the coefficients or the forcing terms to the solution field. If you have a time-dependent PDE like the compressible Euler equations, which is depicted here, the solution operator, for instance, can take the initial datum and then map it to the solution at a later time. So in all these cases, knowing the PDE or knowing the PDE solution is the same as knowing the solution operator. Once you have the solution operator, you can evaluate it, right? So this is the basic idea. And this is what we want to learn from data. And to do so, whenever you have data, you have to make some assumptions. So assume that there is a data distribution, which is going to be a probability measure on input space. Remember that the operator itself takes input, which is a function, infinite dimensional, for instance, a coefficient here, and produces an output, which is a function, again, infinite dimensional. So essentially, this is a mapping between infinite dimensional spaces, which is going to be very important in the sequel. And then what you do is that you put a data distribution, a measure on these input spaces, infinite dimensional input spaces, and I'm assuming that I'm able to sample from this infinite dimensional distribution. And once I sample, I'm able to evaluate my solution operator, either through experiments or through numerical simulations or through analytical solutions if they're available. And then this constitutes sort of the training data. I could put some noise here. So I'm taking the noise-free case for simplicity, but the noise can also be put. It doesn't lead to any technical complications. So my objective now is, given this data pairs, this collection of samples, I'm going to learn about the solution operator, and I'm going to approximate this sort of push-forward measure. So this is the mathematical setting in which I'm going to operate. So essentially, I want to learn an infinite dimensional object, an infinite dimensional operator from data, okay? And how do I do that? So the answer is sort of obvious. We are in the age of AI, and using essentially more GPUs, lots of data, and it's deep neural networks, it's mathematical objects, deep neural networks. we are able to do a lot of things that were hitherto not possible with traditional machine learning methods. So we are going to employ these things to learn the solution operator of the PDEs. But right at the start, off the gate, there are some issues here, right? So if you remember, so my problem essentially is infinite dimensional because I have this infinite dimensional object. But neural networks, I think many of you know this, these are just mappings which take a vector input and produce a vector output. These vectors can be very, very high dimensional. For instance, Zora, the output vector is like millions of dimensions because it's an image or a video. But nevertheless, these are finite dimensional objects. So the caveat here is that I want to learn something which is infinite dimensional, but at the end of the day, I only have access to sort of finite dimensional objects to do so. So at some level, I have to discretize, all right? And this is somehow the core business of numerical analysis. That's what numerical analysis does, that it reduces an infinite dimensional problem to a finite dimensional problem and then tries to solve the finite dimensional problem on a computer. So how are we going to do this? And this act or this field of sort of learning the solution operator, operators in general, is called operator learning. And this is what I'm going to employ to solve the problem. So there are different ways to do this. As I said, this is numerical analysis at some level. So one of the ways, which is very popular, is what I call as learning and then discretizing. Because at the end of the day, you have to discretize. So just to recall, because many people know this, is think of neural networks. Neural networks are just compositions. So they take a vector input, produce a vector output, and they do this by passing the function through these elementary functions, through these compositions or layers as they're called. And at each layer, or hidden layer as they're called, these elementary functions are very simple. So you have a matrix vector multiply, you add a vector, so-called bias vector, and then you apply a nonlinearity, so-called activation function. This is a positive part of a function or a hyperbolic tangent, and you apply it component-wise. So this is a very, very simple construction. Matrix vector multiply, vector addition, point-wise composition, right? Now the idea is that, okay, since we are dealing with infinite dimensional objects, instead of having vectors as inputs and outputs, we have functions as inputs and outputs. Why don't we generalize this construction that we have here to infinite dimensions? And this leads to the concept of what are called neural operators, which were sort of, let's say, formalized in this paper from people at Caltech. Nick Kovacsky was the first author. And the idea is you exactly do the same thing. You have these compositions, but now for each layer, the input and output are going to be functions. So as you can see, these are inputs and outputs are functions. So to evaluate them at some grid points. But now we have to generalize these elementary functions to infinite dimensions, right? So instead of having a vector, you just replace it with a function. That's the natural extension. And now instead of having a vector matrix vector multiply, a matvec, the natural extension, infinite dimensional extension of this is a kernel integral operator. So you have a kernel function, you multiply that with your input function, and then you integrate over the domain. And you can see that when I discretize this object, I'll precisely get a matrix vector multiply. And then in terms of the nonlinearity here, you just apply it component-wise and point-wise. So this is the basic idea. It's a very straightforward extension of neural networks to infinite dimensions. But remember that we cannot evaluate infinite dimensional objects, nor can we compute these integrals exactly, right? So at the end of the day, we have to discretize. And when we discretize, for instance, we discretize on a grid, then when I evaluate a kernel integral, the cost grows quadratically in the number of points, right? Because it's a kernel, it's a quadratic cost. And then we have to care about computational complexity, because if I have 1,000 points, this is a million. But if I have a million points, this is a billion, right? A billion parameters. So it's computationally complex. So I have to choose this kernel carefully. And a particularly attractive choice was made by the same set of people, but that proposed neural operators. But this time it's Zhongyi Li who was the first author. And the idea is very simple. So instead of having general kernels here, what you do is to have a translation invariant kernel. Now, translation invariance is a very natural ansatz if it were for physics. And once you have translation invariant kernels, this becomes a convolution. And one way to evaluate a convolution is to work with in the Fourier domain, because then a convolution just becomes a multiplication. And this was the key idea. So what you do is that at the level of functions, you have a function, you take its Fourier transform. So in the Fourier domain, you multiply a Fourier multiplier. This could be a matrix, for instance. Then you take an inverse Fourier transform, and then you're back to physical domain, and then you apply the nonlinearity pointwise. So the convolution somehow is non-local, it's global. The nonlinearity is pointwise or local in some sense. And the advantage of this, at least on a Cartesian grid, you know that with FFT, you can evaluate the Fourier and the inverse Fourier transform very quickly. So it becomes log linear instead of quadratic. So there's a huge advantage. So it's a very neat construction. It's backed by very solid theory, including from us, and it's very, very widely used. So this is sort of the, let's say, the canonical choice these days in approximating solution operators or PDEs. However, this is not the only way to do it, right? This is one particular choice. Another choice where we have good reasons to make that choice, this was made by us a couple of years ago, and this does local convolutions. So instead of doing convolutions in Fourier space, we do convolutions in physical space. As long as the convolution kernel is compact, then the complexity is scaling quite well. But the difference now is that we work with non-local activations or non-pointwise activations. Why is that? For those who know spectral methods, this has sort of a sense of spectral methods because you're working with in the Fourier domain. And the point is that whenever you work in Fourier domain, when you apply a nonlinearity pointwise, you end up with what is called aliasing, right? This is a big problem in Fourier methods. So just let me tell you what it is. So you have the orange signal. This is the original signal. You apply a ReLU, which is a very common nonlinearity, which is the positive part of a function. Then what happens is that it introduces new frequencies. So the frequency bandwidth increases, it introduces new frequencies, which leads to something called aliasing. And this high frequency information can corrupt or pollute your solution, right? So what we wanted to do was to sort of fight against it. So what we suggested is essentially to do some non-pointwise or non-local activations. So we flipped the script. So instead of doing a non-local convolution, we do a local convolution. Instead of doing a local nonlinearity, we do a non-local nonlinearity. And essentially, the details are not important here, but the idea is that you sort of grow the bandwidth so that you allow this aliasing to be counted. So this is the rough idea. And this leads to what are called convolutional neural operators. Of course, in practice, this is a little bit more complicated. It's sort of done in order to process multiscale information. So you have what is called a UNet. So basic idea is that you split a signal into different scales and you process different scales with different layers and you patch them together. But this is a detail. It's really multiscale information processing. So you have these two sort of routes, but there are many, many other routes. And let's see what happens when we use them in practice. So this is a very simple experiment. So you take the Navier-Stokes equation in 2D, just for ease here. And this is the exact operator. So you have some velocity field that is being transformed. You can also view it very well in vorticity. So you have this vortex layers, the shear layers, and then this leads to the excitation of vortices. It's not a very difficult problem, but it's something to look at. And then what we do is that, of course, we have to sample it at a certain grid resolution, right? We can't learn in infinite dimensions. So here what we did is that we sampled everything at 64 squared, just as an example. And then we computed the errors with FNO, Fourier neural operator, and CNO, convolutional neural operator. They do equally well, right? But that's not the objective here. Remember that at the end of the day, I'm evaluating operators. So my input and output functions can be at any resolution, right? Because one particular resolution is for training, but at evaluation, I can use whatever resolution I want. And an ideal operator, learner, should learn how to generalize across different resolutions. And this is sort of a key requirement. And this is what is shown in this plot here. So if I change the test resolution to 128 squared super resolve, or if I take 32 squared sub resolve, you can see if I take a plain UNet, then the error just blows up. It doesn't generalize very well. Even with FNO, you see that it's much better in some sense. The error reduces, but it's still non-zero. Means there is still error when I change the test resolution. So it hasn't really learned the operator. It has just learned a particular finite dimensional representation for it. But because we did this local convolution with non-local nonlinearity, and there is some theory, some math behind it, we see that with the CNO, there is a seamless sort of resolution across grids. And this is because essentially commutative diagrams, there are some commutative diagrams, because what we did is we learned and then discretized, but it's equivalent to when we discretize and then learn. So there's some resolution invariance, some representation invariance that comes in. And this is guaranteed by the sort of convolutional neural operator that I just suggested. So this is one sort of example that in machine learning, the key is not what you do, but what you generalize to. And this is one particular manifestation of that. So this is the story when it comes to having linear kernels, because whether it was CNO or FNO, at the end of the day, we were doing some convolutions, and this was a linear kernel. In principle, you could ask what happens if you generalize the kernels and you work with what are called nonlinear kernels, right? Because what stops us from using nonlinearities here? And one example of this, there are many, many different examples, is what is called operator attention. This is the sort of backbone behind transformers. Attention is a mechanism by which, or a particular mathematical operation behind transformers, which are the most commonly used machine learning architectures these days. And this is exactly something that can be generalized to operators. And the idea is actually very simple. So remember that my kernel is now going to be a nonlinear operation. It depends on the data itself. So what you do is that with a linear kernel, what we would have done is that we would have accumulated information from neighboring points, or let's say from all points in the domain, and we would have weighted them in some learnable manner that is independent of the data, right? But what we do now is that we have this weighting. So this is a weighting of the neighboring points or all points in the domain essentially. And then to compute the weights, we do another operation, another all-to-one call, and we compute how much of a weightage does each of these points have towards the effect that it plays on the update here. So essentially, it's a probability. That's why you see that there is a softmax here. And the idea is that you sort of learn correlations in the data. So at different points might have different importance, different weighting factors, and this you sort of combine them together. But this is a very natural way to do it, right? So you have a nonlinear kernel, and in particular, if you take some fixed weights, then you get back linear kernels. But in general, this can be much more general. Of course, you pay a price, right? Because I'm doing an all-to-one, and then for each all-to-one, I'm doing another all-to-one. So when you combine these operations, the cost becomes quadratic. And I told you that quadratic is not good because this is tokens of points, because in 2D or 3D, this becomes humongous. This is a very, very big number. So we cannot use it just like that in its native form. So we have to do some simplifications, some compression, and so on. And here we are inspired by images, right? Computer vision is about images. So we are inspired by images. And in images, you have something called vision transformers. And the idea is very, very simple. So anyone doing numerical methods would be familiar with the idea that instead of looking at point values, I divide my domain into cells, or in the parlance of computer vision, these are called patches. These are these white boxes that you can see. And instead of sort of applying this attention to the point values themselves, I accumulate them inside each through an average. It could be a cell average in a finite volume method, but in machine learning, it's a learnable average. So you just apply things to learnable averages, and then you get what is called a vision transformer. And the advantage is now that the scaling is not with respect to the number of points, but it's with respect to the number of patches. But the problem is that sometimes, to get reasonable accuracy, you can't take too big cells. You have to take small enough cells, right? This is something that we know from finite volume methods. So again, this doesn't scale very well. So one does another level of, this is not my work, this is from computer vision, that they do another level of, let's say, discretization or coarsening. So this is really a multi-level discretization. So you have these white boxes. These are the patches or cells, cell averages. These are the objects that we're using. But then we do a coarser discretization. These are these black boxes, which are called windows. So essentially what you do now is that you apply attention. So this is this non-local kernel or non-linear kernel, not to the individual cells for the entire domain, but you just localize them to each of these windows, to each of these black boxes. So of course the scaling is okay now, right? Because you just have to scale according to the number of windows that you have, according to the number of subdomains. So there's a domain decomposition method essentially. Unfortunately, now there's no global communication, because before we had said that global communication is good, and this is the advantage of having this nonlinear kernels, but now they're not talking to each other. But this is where the ingenuity really comes in, because remember that these neural networks are stacked on top of each other. And so what you do is that in the next sort of layer, you just shift the windows. So for instance, this point and this point, they were never sort of talking to each other. There's no global information transfer. But when you change the windows, there's an automatic global information transfer. And when you do this iteratively, you can sweep through the entire domain. So you have global information processing, and at the same time, you have very good scaling properties. And this is the architecture that we sort of adapted towards operators for PDEs. And these are called SWIN, or shifted window transformers. And this leads to something called a scalable operator transformer. So this is the object. So again, you have multi-scale information processing. You sort of decompose the signal into different scales and you process them individually. This is more of a detail, right? And this has all the nice theoretical properties that FNO had or CNO had and so on. But at the same time, it has a transformer, so you have global information processing. In practice, though, at least if you apply it to different examples, these are some very simple examples. This is just Poisson's equation with some Gaussian forcing. And then you see that it's slightly better, but for some other problems, it is comparable. So essentially, despite sort of the basic nature being quadratic, you have exactly the same complexity in terms of linear kernel methods, CNO, FNO, and so on. But at the same time, you don't really have any gains in accuracy at the moment. You'll see that changes later. So essentially, and this we have tested for a bunch, and not just us, the entire community has tested on a bunch of problems. So the bottom line here is that if you have 2D Cartesian domains, then machine learning models are able to learn very well. The errors can be very, very small. Some cases they are large, but essentially they're in the 1-2% range. So you are in a good shape. But again, this was the giveaway, right? I said 2D Cartesian domains. Now, all of us who work on problems inspired from engineering, we know that that is not the case. Means PDEs on Cartesian domains are just model problems, right? When you want to do it. So this is a situation that I've just described. But in reality, even in 2D, if you do flow past airfoils, something that I'm very interested in, you have very, very complex grids. You see, this is an actual grid which is adapted to fit the shocks and so on. And 3D, of course, if you have a car and you want to sort of look at the surface of the car, then you have very, very complex grids. So you have to sort of, let's say, extend this methodology to be able to deal with arbitrary domains, in particular unstructured grids or even point clouds, right? So we need to handle such data. Otherwise, our problems have limited, or our methods have limited practical utility. So yes, and this is sort of an increasingly sort of, let's say, growing field of research, how to adapt these methods to non-Cartesian grids, to complex grids. And one way that you can do, a very natural way, is to use graphs, right? Because at the end of the day, you can sort of, whatever point cloud that you've been given or whatever grid that you've been given, you can sort of subsume it within a graph, even a very complex grid on a three-dimensional car. You can subsume it on a graph. And it turns out that on graphs, you have something called graph or geometric machine learning that can be very, very useful. So the idea is very simple. So you have a graph here. I don't know how well you see it, but just imagine that these are just your grid points organized based on some nearest neighbor connectivity. And then at each node of the graph, you have some features, temperature, pressure, displacement, whatever, stress, whatever you want to. On the edges also, you can put some features. This could be gradients, for instance. And what a graph neural network does is that given data on a graph, so data is given on the nodes and edges, and potentially even global features, it sort of transforms it by using neural networks to sort of updates it in each layer. And it is done by a mechanism which is called message passing. It's a very, very simple mechanism. So you have you want to update the node feature here, for instance, temperature at this point. You look at its neighbors, you collect information here, put them through a neural network for some processing, then adapt them or sort of aggregate them by a sum, for instance, or a max or something like that, and then put another neural network to sort of process it further. And this is message passing. You collect messages from the neighbors, and then you update your state. It's very, very simple. And how you choose these neural networks gives you a whole panoply, a whole zoo of graph neural networks. So there are many such examples that are available. One particularly recent one that came out from a lab, the paper is available on arXiv. It's just a couple of months old. It's called Rigno. It's just doing this on steroids. So I don't want to describe all the details here. So you get a point cloud, which is given here, and then you do this in this multiscale manner. So you have these graphs, and you sort of evolve things along the graphs, and then you come back. So this is essentially the same multiscale information processing, except that each component is going to be a graph neural network. And there are many, many modifications because you want resolution invariance, you want temporal continuity, and so on. But the bottom line is that you get something which is very, very sort of flexible. So you can work on a circle, you can work with an airfoil, you can work with a very complex domain. So this is plasticity. You can sort of deform the domain and so on. And it works very well. So very, very flexible. You can go far beyond Cartesian grids. It's also very accurate. There's a bunch of numbers here. It's very, very accurate. You can see that always it's the most accurate method that is out there. But of course, the problem here is that because it's based on graphs, and graphs, particularly when they change, so graphs, remember that it's sparse memory on a GPU. You have to make repeated sparse memory access, and you can't hard code a lot because the graphs can change. For instance, if you're working with plasticity or if you're working with airfoils, the shape of the airfoil changes, so you cannot really hard code elements of the graph. So it's not very efficient. So for instance, for some of these results, particularly for time-dependent problems, this takes us more than 2 days of training on a GPU, which is just, so you really can't scale it. So there's a problem. It's very expressive, very good, mathematically very general, but in terms of efficiency, you suffer something. On the other hand, so what do you do in order to increase efficiency? There are ways, but the one that I'm going to sort of present here a little bit is to use graphs, but only as a component, and to use transformers otherwise. And this leads to what are called geometry-aware operator transformers. So what you do is that your original grid is on a graph, and you collect information using graphs, and you project it onto a latent grid, which is a Cartesian domain. Because Cartesian domains you can transform, or you can sort of process information very, very quickly by using transformers. So the bulk of the compute is on the Cartesian domain. Only the encoding and the decoding, as we call it, is on this unstructured domain, and this is done with respect to graphs. So it's sort of a combination of graphs and transformers. This is as accurate. It's not more accurate, but it's as accurate, but it's much, much more efficient. A factor of 20, 30, 40, 50 times more efficient. The same problems that took 2 days takes about 3 hours. And these are some of the numbers. And this is an architecture that we can really scale for, so let's say industrial scale problems. And let me give you an example. So this is an example from MIT. People, they have this challenge where they have done CFD for 8,000 different car shapes. You can see different kinds of cars here: hatchbacks, sedans, coupes, sort of all kinds of different car shapes. And they want to compute, or they want to predict things like surface pressure, surface wall shear stress, and so on. And actually, we can sort of use this architecture that we have, geometry-aware operator transformer, and we get very, very good results. For instance, to predict the surface pressure, given a car shape and given the flow conditions, and even the wall shear stress, these are predicted to very, very accurate results. And needless to say, this is also sort of state of the art, particularly for the shear. We are quite a bit more accurate. And this is not just accuracy, but it's the scalability. You know, there are these are, for each car shape, we have 500,000 points, and we have 8,000 car shapes in training. So this is quite a bit of computational challenge. And this is managed because we have this judicious combination of graphs and transformers. So this is an example where you can sort of, let's say, scale machine learning architectures to do real industrial problems. And this is an advantage here. But of course, there are challenges. So let me up the ante a little bit more and say, can we deal with the hardest PDEs that somehow I know, right? And these are essentially the equations of fluid dynamics. And the reason for that is because you have multiscale structure, you have lots of different scales, and you also have the solutions are chaotic. So let me give you an example of this. So this is 3D Navier-Stokes at very high Reynolds number, and my initial conditions correspond to what is called the Taylor-Green vortex. So Taylor-Green vortex is a particular initial condition that leads to a turbulent fluid flow. And what you see up here is 3 realizations of tiny little perturbations of the Taylor-Green vortex. So as you can see, there are lots of, this is the kinetic energy sampled at each point, the amplitude of the kinetic energy. And you can see that there's a lot of fine scale structure. And also, despite these tiny little perturbations, because it's a chaotic system, you get very, they look the same, or they look qualitatively the same. But if you focus, for instance, at this point, you see that the solution changes quite a bit, right? So there's a lot of variance for very tiny perturbations. Now, this is on a Cartesian grid, so I can take my convolutional, Fourier, whatever neural operator. I have actually a mix of both. And then what you see here is 2 things. First of all, the small scales are completely smeared out. So you see, you don't recover any of the small scales in the flow, only the large scales. And second, you don't see the variance at all. You know, it always gives you the same solution, right? So it's sort of, it regresses or collapses to the mean. And if it's not a question of a particular ML model, you take any ML model, including the ones that I just touted, and you end up with the same situation, that for these kind of problems, which are chaotic and multiscale, almost no machine learning method works. And why is that? So there is some mathematical understanding now of this. There's a very recent paper from my lab together with some collaborators at Google. So what we did is we understood that this is primarily because neural networks, these are very nice objects, but when you train them, you end up with things which are sort of stable, and there is a reason. So if you make tiny, tiny perturbations, you see some small changes, not a huge change. These are not really chaotic. This is because it has been well established that trained neural networks are somehow at the edge of chaos, which means that the Lifshitz constant is bounded. It's not small, so you can represent quite a bit of functions, but at the same time, it's not infinite. So it's still bounded, and it's also related to what is called spectral bias of neural networks. But essentially, when you train neural networks, you use stochastic gradient descent. So the gradients have to be well behaved. And if the gradients are either infinitely large or infinitely small, you are in trouble, right? So that's why this assumption comes in. But this is what is detrimental to us, because what happens, and this is a 2-bit of math here. So I want to approximate, I take these tiny, tiny little perturbations, and then I want to sort of compute statistics across them. So this is my exact solution operator. This is what the neural network has. So it gets this tiny, tiny little inputs. But the exact solution operator, you cannot simply say that they are closed, right? It's a chaotic system. So this remains where it is. On the other hand, the neural network, because it is insensitive to small perturbations, it goes back to this U star here. And once you have this, you can sort of do what is called a bias variance decomposition. So you divide it into two terms. So essentially, this term here is independent of theta. Theta are the parameters of my neural network. This term is independent. At best, what can happen is that this guy equals to this, right? Because these are quadratic, so this is a positive number. So at best, this term can be 0. So what does it mean? First of all, when I'm trying to approximate this quantity, I'll have large errors if my variance is large, right? If my variance is large, this is going to be large errors. Second, this will always collapse to the mean, because this is precisely the mean of this distribution. So essentially, what we observe is what we can prove in an end-to-end manner. So neural networks, when they're trained to minimize this least squares or the mean absolute error, they're never going to work for this problem. So what can we do? Well, this comes back from some of the work that I did back in the day, which essentially says for this kind of chaotic systems, if you try to learn the map itself, the operator itself, this is useless. At best, what you can learn is a distribution, a statistics over the outputs, because these are so chaotic that tiny changes and you see that there is a huge spread here, right? So essentially, statistical computation is the only thing that is feasible, which means that at best, I can approximate the conditional distribution directly without having to go through this solution operator itself. So then how do you learn a conditional distribution without going through the solution operator? It turns out that machine learning models are actually quite good at it, because all of us have used DALL-E or nowadays ChatGPT. And if you give it an input prompt, Fox looking at for his ox, and it will generate an output. So it will sample something from a distribution conditioned on this input prompt, right? So essentially, this is the advantage. And there are many, many different ways to do it. Potentially, the most popular one is what are called diffusion models. And what diffusion models do is these are essentially transforming a distribution, let's say the target distribution, into some known distribution, which is typically Gaussian, right? So when you sort of train, you add noise, and during test, when you try to infer, then given a Gaussian distribution and given this input, you are going to get some nice sample. So this is the basic idea behind the diffusion model, that you keep on adding noise during training and you denoise essentially at inference in order to get a conditional sample from the distribution. It can also be done by flows. Flows are another way to transform a target distribution to an unknown distribution to a sort of a known distribution. So that's the basic idea. And I'm running out of time a little bit, but what we did in this paper is that we took these algorithms, which are out there, and then we were able to scale it or adapt it to our problems. And so this is a score-based diffusion model. So essentially what happens during inference is that you are given the initial conditions, you are given the Gaussian distribution, essentially noise, and then you produce the flow field, right? You produce the flow field, and this is done by solving this stochastic differential equation, something called a reverse stochastic differential equation. And the drift of this stochastic differential equation is what is trained. So this is what is called a denoiser. So during the training process, I have a clean sample, I have the initial condition, I add noise by a certain noise schedule, and then I denoise it by using machine learning, a neural network. The same kind of neural network that is insensitive is also used for the denoiser. But now, because we are somehow adding noise iteratively during the sort of the solution of this SDE, we can even prove, at least in some simple cases, that it approximates the correct conditional distribution. So there is it's not changing the neural networks, but it's changing how you train them. You train them to do this denoising. And once you do that, the same thing that didn't work works like a charm now. So for instance, here you had the list of vorticity. With our previous approach, we didn't have the small scales. Now you can get the small scales very, very well. And you can see that sometimes you can't distinguish between the flow generated by the AI model and the flow that is the ground truth of the flow. And similarly for the statistics, and just to give you an example of how dramatic the gains are, so earlier the spectrum was just washed out. Now the spectrum matches very nicely. And earlier there was no variance because everything was collapsing to the mean. And now with this new training, with the same kind of neural network, we are able to sort of get the right probability distribution. So this is, I think, at least an achievement in that sense. And you can really scale it to real world flows. So for instance, this is a nozzle flow. This is something from the atmospheric sciences with shock waves and so on. And they do very well. But the point is, what we gain is, to generate sort of the ground truth here, it took us several hours, by different methods, anything from 3.5 to 15 hours, 14 hours. Whereas at inference, once you have this trained model, we can do it in a second or two. So this is a big, big advantage that you have orders and orders of magnitude gain, and you really can sort of go for very, very complex fluid flows, and you're able to do that. But okay, I'm just extolling the virtues of machine learning here. But what is the catch here? What is the caveat? In the last 5 minutes, let me just focus on that very, very quickly, and then we can have some questions. The main point that I want to focus on is that all these methods, they come with a price. And the price is in terms of the number of samples, number of training points that are needed in order to get good performance. So these are different methods that I just described, graphs, convolutions, transformers with diffusion models, and so on. The bottom line is that as you increase the number of training samples, you get better and better errors, right? So for instance, here, if you had 10,000 samples, you get 1% error. But the problem is the theory as well as empirical practice tells us that these rates are low. At best, they're 0.5 because that's central limit theorem. But in practice, they're lower. Also in theory, they're lower. And what does that mean? That means that for per task, whether it's a diffusion model or whether it's a transformer, whether it's a graph, for each of these learning tasks, you need anywhere between 1,000 and 10,000 training samples. And this is okay if you are crawling the internet for data, text or images, but in our profession where we have numerical simulations and experiments, this is unaffordable, right? So, and this is the big, big problem, that there is a caveat here. If I have enough data, then I know that I can learn something. But the problem is I don't have enough data. So how do I make this model scale better? So this is the big, big challenge in my opinion. And in a way, this challenge has been there for a long time. And if you have a very sophisticated AI system like ChatGPT or Gemini, they also have to deal with it. And the way they deal with it is because they use what are called foundation models. Now, foundation models are a very different kind of a machine learning framework. What you do is that you have a big neural network, but that is trained on very, very diverse types of data. So for a Gemini or ChatGPT, this could be images, text, signals, and so on. And then this learns some useful representations, some useful relationships between the data. And then finally, when you look at a particular task, like answering a question, then it is adapted, for instance, through prompts in order to answer that. So there's a two-stage process. There is something called pre-training, where it learns these representations, and then there's adaptation or fine-tuning, where it is sort of adapted to the particular task. Now you can sort of think of it for PDEs. So now we have all kinds of PDEs, right? We have Poisson's equation, wave equation, heat equation, Navier-Stokes. For each of there are infinitely many of them. For each of these PDEs, you can change boundary conditions, initial conditions, and so on. So there are sort of infinitely many of these. So you can end up getting an entire sort of zoo of operators. So what a foundation model can do is that it can take different PDEs, different operators, get pre-trained, and then when you're evaluating a particular task, it can take a particular operator corresponding to a particular PDE, which it might or might not have been trained for. And then you try to adapt. So that's the basic idea. But of course, you will ask me, and I ask myself, that when I learned PDEs, You have sort of elliptic equations, parabolic equations, linear equations, hyperbolic equations, nonlinear equations, and these are all silos. So what good is it going to do to me to learn on Poisson equation and to test on Navier-Stokes, or vice versa, right? So this is sort of a priori unclear, but of course one has to try it out, and this is what we tried out, and what came out is a foundation model for PDEs. It's called Poseidon. It was released at the end of last year. The code is available, the models are available, you can sort of test for it. And I should really wrap up. So what I want to say is that it's based on transformer, this scalable operator transformer that I just described. And it's based on pre-training. It's a small scale model. So it's pre-trained on just two PDEs, the incompressible Navier-Stokes and the compressible Euler equations. And if you look at a summary, it has something like 5 million image pairs. So it's not a lot of data, but it's something to start with. And our biggest model is something like 630 million parameters. So it's still a small scale experiment. But how do we know that the experiment succeeded or failed? We have to try it out. So what we do is that we trained only on the equations of fluid dynamics, Navier-Stokes and Euler. But a test, what we can do is we had the same equations again, but we also had other tests. For instance, we added Navier-Stokes, transport to Navier-Stokes, or gravity to Euler, and sometimes we took completely different equations like wave equation or Poisson's equation or Helmholtz equation, which are not seen at all during training. And did this model work? Well, to measure it, what we did, so in order to sort of implement it, we had to use something called fine tuning, but I'm sort of out of time to describe this. But to measure it, I looked at two metrics. So we looked at two metrics. One is how fewer samples do we need compared to what we had before. So this is a gain in sort of sample efficiency, right? Because earlier I said that I don't have infinite amounts of data. I have to reduce the amount of data in order to get a certain acceptable error. And this is the gain that I want to quantify. And the second one is how much of a gain in accuracy I have if I have the same amount of data. And it turns out, and I don't want to give the full result, but a summary, that it worked remarkably well at this small scale. So in particular, I'll give you an example. The large model was 50 times more sample efficient than FNO, which was our baseline model. So instead of having 1,000 samples, you could get the same amount of error with 20 samples. And this is, if you can scale it, and if you only require 20 samples on an average, then somehow we solve this sample efficiency problem. But of course, this is still small scale. Similarly, we gained a lot in terms of accuracy. So I'm sort of running out of time to describe why it works, but maybe if there are questions, I can take it. So let me just summarize. So in particular, so this is a proof of concept. It shows that yes, there's a potential of leveraging different physics, different PDEs, in order to sort of reduce the number of samples that are needed for a particular task. And the promise is always cost, right? Because at inference, this takes almost no time. So essentially what we showed is that there is some feasibility to these foundation models. Even though these things are hitherto not connected to each other a priori, what we discover a posteriori is that probably PDEs are much closer to each other in some sense than they were thought before, right? And it's of course being used, but maybe what we're doing now is to sort of expand the range here, expand the scale, scale the model, scale the data set size, add all these features that I talked about, 3D, diffusion, point clouds, and so on. And there are some preliminary positive results. But let me sort of finish so that we can have a couple of questions. So my basic point was that nowadays you could say that if you have PDEs and the solution operator of PDEs, there are machine learning models out there which can very accurately represent it, provided that you have enough data. I wouldn't have said this 1 year ago, but now there is a whole zoo of models that are able to do different things. So you have graphs and transformers for arbitrary domains. You have diffusion models for very complex PDEs. But the main challenge is sample efficiency. So the point that I'm making is that if you have a lot of data, this works well. Like in weather, it works very, very well. There's a lot of data. But sample efficiency is still a challenge. One route to address it is through foundation models. There are some preliminary attempts. But in the next 3-4 years, I expect that this will be scaled up tremendously. And once it is scaled up, then we can sort of realize the full potential that machine learning has in sort of in the context of solving PDEs or in scientific computing or in physics. But these are exciting times, and I'm sorry of overshooting the time a little bit. I had too much of content, which I realize now. But nevertheless, I try to give you a glimpse of what's going on. And thank you very much for your attention.
Great. Thank you, Sid, for a very fascinating presentation. Is my camera? Can you hear me? Because I just unmuted.
Yeah, I can hear you.
Yeah. So I have a bunch of talks, sorry, a bunch of questions based on the talk, but also some that are maybe not so directly related to it, where I'm curious about your opinion on things.
Yeah, please.
But I think maybe we should start with that. So I guess the first one is a bit more general. So where do you see the future of this particular area of applied mathematics going?
Very bright. Very, very bright, because I think that together with sort of efficient numerical methods, if we can sort of train foundation models and if we are able to sort of, then we can solve problems that were, for instance, some of these race car simulations I didn't show you because I don't have the permission to show you, is it takes, I don't know, 1,000 node hours, but with a well-trained model, this can be done in less than a second. And then you can sort of go through the design space, you can explore it very, very efficiently. So there's a lot of I think the future is very, very bright. Of course, there are a lot of challenges, right? So this is, I try to sort of explain some of the challenges. They're being overcome in a step by step manner. But I think the key challenge is, can we work in sort of a data deficient regime, in a data scarce regime, or data sparse regime? And I think there are some promising routes on how this can be done. But whether this works out or not is sort of, I bet on it, but in my research, but the jury is still out, right? But I see it as a very, very bright future, not just in terms of number of papers that are being written, because a huge amount of number of papers are being written, but that doesn't. But I think slowly we are on the cusp of something that can be scaled, and that's the key point somehow.
Yeah, thank you. So I have going in that direction, a bit more of a critical question,
Mhm.
based on something you mentioned earlier in the talk about learning new physics. So
Mhm.
what are the success stories for actually learning new physical models that we don't already know? Or if we haven't been able to do that yet, what are the big roadblocks?
I think this is a very, very good question. So first of all, if you have a lot of data, like in weather, then there is a lot of data, and this is sort of well known that the AI-based predictors or forecasters are as good or even better, particularly at nowcasting and so on, than the conventional numerical methods. This is just a fact, right? So that's a big success in some sense. But also, I think if you have inverse problems and so on, I didn't have the examples, but in particular, inverse problems, I mean, sometimes with our traditional PDE-based techniques, we're simply not able to get a good solution. Whereas with these methods, we somehow are able to do much better. So for inverse problems, for uncertainty quantification, I think for design in general, there are things that were simply not possible. Slowly they are getting possible, right? Because I think the challenge is the lack of data in many of these domains. In those domains where there's a lot of data, like in weather and climate, this has already been successful. In other domains, we have to work harder, we have to build foundation models, learn, leverage other data, and then try to push. So I think we will be able to do things that were hitherto not possible. For instance, doing uncertainty quantification on some of the flows that I showed you was not possible before, I would say. For instance, this one, it takes about 4 hours, and if I take 1,000 samples, maybe this is not even good enough. And then now I can do it in no time. It's sort of, so there are some success stories in that case.
Yeah, interesting. So I'm curious about another thing, a bit more of a technical question. Um,
Yeah.
so a lot of these operators, these neural operators, and these things that you're learning are for partial differential equations.
Mhm.
And the solution map between the parameters to the state is generally understood to be differentiable, at least after you discretize it and you have this finite dimensional model.
Yeah.
But what about for non-smooth operator equations like variational inequalities or optimization problems? Have you tried anything like that?
Yes, well, I think that's a very, very good question. Let me give you an example, maybe, and then you see that it's you don't have to have. So all that we need is that the operator is continuous.
Hmm.
As long as it is continuous, a neural network in principle can approximate it. But it can be very, very complicated, right? Some of these things are, the operator itself is very, very complex. Maybe I showed you again the diffusion model. That's the one which has the most complex operators. You have shock waves, you have all kinds of turbulence, you have some interaction between them. And the operator itself, the neural operator, is completely agnostic. I have not given it any information that this comes from a PDE and so on and so forth. So there is absolutely no reason why variational inequalities, even inverse, I didn't have the slides to show you here, but even mappings for inverse problems, these are like Dirichlet to Neumann maps and so on, even these are sort of well approximable. So absolutely no reason to believe that this is, of course, if the operator is not even measurable, then we don't stand a chance. But then I think as long as the operator is continuous, even if it's sort of ill-behaved, like right, these maps, as I showed you, their Lipschitz constants are far out, and
Right.
still we are able to learn something. So there is absolutely no reason why, to the best of my knowledge, that I don't see any physical system if you have enough data. That's why I keep on emphasizing this data aspect, right? So
Yeah.
if you have variational inequality or some optimization problem, I don't I don't see why in principle this can't be done. I haven't done it myself because I don't have the data for it. But given that we can generate a turbulent fluid flow, there's absolutely no reason why we can't solve a variational inequality.
Yeah, I was thinking about if you like frictional contact, right? Where in
Mhm.
fact it's a quasi-variational inequality, right? So you basically have a map that sort of pushes the initial solution through a fixed point iteration, and at each iteration you solve a variational inequality. But if you have the solution map for that variational inequality, then there might be another way of looking at.
Potentially. So you have to bake that in probably. You have to
Yeah,
bake in the
yeah,
iteration through the training process. I think then it's possible.
right. And I had another technical question. So in a lot of these problems, you have integral operators, and
Mhm.
this one with operator attention, it was called. There was integrals inside the integrals and so on.
Yes.
Do you have any issues with the high dimensional quadrature? Because I'm assuming D could be potentially high dimensional.
Yeah, but these are all done more or less randomly, right? So it's
It's all, it's all Monte Carlo or quasi Monte
It's
Carlo.
mostly Monte Carlo, but you see here that the integration itself is just on the physical domain,
Hmm.
is not on the parameter domain, right? So it's always on the physical domain. So
Ah,
he,
okay, okay. So
even though we work with we use Monte Carlo, but I think this is not an issue. What you are talking about is sort of very high dimensional PDEs, for instance, with high dimensional physical domains. There, Monte Carlo comes to your aid. You don't really care about anything other than Monte Carlo. So I think that's the sort of point. I
yeah,
don't think quadrature is an issue.
yeah, okay, interesting. Ah,
I
so
think
there's a question.
there was a talk on the chat.
Yes, there's a
Let me
question.
try to see. Sorry.
You see it?
Yeah, it's not that easy for me to. Okay, now I see something. Q&A. Yeah, it's
I could just
for
read it.
what references, books or papers and mathematical techniques would you recommend for getting started? Yeah, this is there are not many. So there is a well, I'm supposedly writing a review paper, but I think it should be available at the end of the summer. There will be a review paper. But I teach a course on this. It's called AI in Science and Engineering, and all the lectures are available on YouTube. So if you just Google me on or my lab on YouTube, you will get the lectures. Many people actually use them. These are sort of popular. Otherwise, we have a book recently. It's called Numerical Analysis and Machine Learning, where a lot of people have contributed. So that could also be a resource. But I accept that there is no sort of a consensus on what's a good reference. But I'm writing a sort of a review paper, and I think it will be available at the end of June. At least it will be from sort of containing some of the things that are there in the talk. So it will still be biased, but at least comprehensive.
Yeah, excellent. We're all looking forward to that, definitely, because I've asked myself the same question. Where do you even start, right? If you're not from this field, and it would be nice to
But I
have.
think the lectures, the YouTube lectures are sort of, they are popular. So, sorry. Yeah.
Yeah. Great. Then, if that's it for questions, I'm all done with my questions. Oh no, wait, there's one more. It says
No, it
Balthasar.
just says thank you.
Oh, one
No,
one of the attendees raised their hand. Balta, you have to ask your question in the Q&A.
I think it's not possible to unmute them, right?
No, it's not.
So it's sort of.
Okay. Well, our hour is up, so I think we'll just have to go on without it. But thank you very much, Sid, for this incredibly fascinating talk and discussion afterwards. And for
Thank you
everyone
very
who's,
much and have a nice day.
yeah,
Ciao.
you too. Thank
Bye-bye.
you. Bye-bye.
Bye-bye.